In this lecture, we are going to do a basic review of the idea of a determinant and the mathematics associated with determinants. Determinants show up a lot in the study of the exterior algebras, and all the exterior algebras have rules that handle the operations of their elements, their inner products, their relationships with each other. The determinant just shows up so much in that I feel like it's necessary to do a nice review of the determinant before we actually proceed into a deeper study of these exterior product spaces and the total exterior algebra. So I want to begin with something that we have probably seen before. Everything about the determinant is something you've seen before. It's come from algebra, right? We learned how to create the determinant. You know, if we were given a matrix, A, B, C, D, E, F, G, A, B, C, D, H, I, let's see, right? If we had a matrix like that, we all kind of knew, okay, to calculate the determinant, we multiply this row together, and then we multiply that together, then we multiply those together. And then from that, we subtract the product of, this row multiplied by that, multiplied by that. And we subtract all those together, we get a number we call the determinant, and that determinant was important in solving linear equations. And all that's true, and all that's right. Problem, of course, is that we're going to use bigger, J, K, L, M, N, O, P, right? We're going to use 4x4 matrices, if not even bigger. And in principle, you should be able to do this for any size matrix, and, we don't know exactly how to do that calculation. So we're going to kind of go through a lot of that stuff. But I want to sort of get to the meat of it in a sense that I want to understand the determinant as something that's involving the area that's enclosed by two vectors. So let's consider this a plane with E1 and E2 as two different vectors. And the first vector, I guess we'll call, we'll call it A, and then we'll call this one B. And so A will have components A1 and A2, and B will have components B1 and B2. Right, and now I want to consider the area of the parallelogram that is formed with those two vectors are the sides of that area, of that little region of space. So this space is R2, right? It's just in the plane. And so we could look at this and we can say, well, let's just do the geometric construction. I know that that area is going to be this distance here multiplied by this height there, and I might suggest that this angle, the angle between, say, this line here and the vector A, we'll call that angle theta, and then we'll call this, so that angle's theta, and we'll call this angle phi. Okay, that should work. And then we'll start trying to calculate what the area of this element is. So we know that the magnitude of this line here, this green line, the magnitude of A, right, that's going to equal the square root of A1 squared plus A2 squared, right? And for good measure, the magnitude of B is going to be the square root of B1 squared plus B2 squared. We know that, we know that the sine of theta is going to be A2 over the magnitude of A. And we know that the sine of phi is going to be B2 over the magnitude of B. And I guess we need the cosines too, right? The cosine of theta is going to equal A1 over the magnitude of A, and the cosine of phi is going to equal B1 over the magnitude of B, something like that. And so what is this area? Well, this area is this distance here that I've mentioned before, multiplied by this height. Well, that height is going to be the magnitude of b times the sine of phi minus theta, right? So this height, I'll call it h. So h equals the magnitude of b times the sine of phi minus theta. And the sine of phi minus theta is the sine of theta times the cosine, the sine of phi minus the cosine of theta minus the cosine of phi times the sine of theta, right? And so that that substitutes in here. So then I need h times the magnitude of a, which is going to be b, the magnitude of b, times the magnitude of a times this thing, sine phi cosine theta minus cosine phi sine theta, right? And then I just put in these substitutions here, and I think you can see what's going to happen, right? This cosine will put the cosine will put a b in the denominator here. The sine will put an a in the denominator here. Likewise, you'll get an a and a b in the denominator here, and that'll cancel that out. And then all that you'll be left with is these numerators. And so this is going to be, let's see, sine phi will be b2 cosine theta. Let's put that one up front to be suggestive, minus b1a2, which equals the area. That's this area here, right? This area. So the area actually is easily expressible in terms of the components of the two vectors here that describe the edges, right? And what's important to see there is that if we created this matrix that looked like A1, A2, B1, B2, the determinant of that thing is equal to A1, B2 minus B1, A2, which is equal to the area. And I'm counting on the fact that you know how to take the determinant of a 2-by-2 matrix, right? That's something you should know. And but the point is that the area of the parallelogram that is enclosed when two vectors are describe the edges is the determinant of this thing, right? And it turns out this is true for any dimension, right? If I added a third vector, right, and I told the story like this, I had an A, and we had a B, and then there was some sort of C involved, right? And I kind of drew what would be a, what would it be? It would be a parallelepiped, right? And it would extend out in 3 dimensions, something like that, right? Well, I guess those would be visible lines. So, but the volume of this thing, the volume would equal the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3, right? And that's true for any dimension. So any number of dimensions, the volume element of the parallelepiped that is formed by a collection of n vectors, so if I'm working in n dimensions, I will always need n vectors to do this. That volume will always be the determinant of the matrix where you fill in the matrix with the components of all those vectors. And this makes a lot of sense, right? I mean, because you know that in the 2-dimensional case, right, as this angle goes to 0, right, as this angle goes to 0, that volume should go to 0, right? That area should get smaller and smaller until they're coincident. When they're coincident, it's all 0. And that's the equivalent of saying that 2 of these rows are not linearly independent, right? This row might be is just a factor different than that row. And the determinant in such a case goes to 0. So the determinant actually makes a lot of sense in regard to this notion of a volume element. So that's the first thing we needed to understand, is that the determinant always represents a volume element. And in the context of what we're doing here, when we're talking about vector spaces in the abstract, right? So you might say, well, wait a minute, we've never done this before. We've never drawn little vectors out on a sketch like this before. But in some sense, we have, right? This point here, you might think of as representing something that's attached to the space-time at a certain point, right? So this is attached to the space-time. So if this is the space-time, and here's a point in the space-time, this is really the tangent space, right? This is our tangent space, right? And these vectors here, E2 and E1, so if we're going to call it a tangent space, and if we have coordinates on the space-time, then these things are really partial 2, partial 1 in the coordinate basis, right? And it's like, I realize it's abstract in the sense that you can't marking out differences when we're labeling the axis with a differential operator seems weird, but if you want to think of it, just think of this as just the value of the first component of a vector that lives in the tangent space described in the coordinate basis. And that's perfectly fine. That's what these marks really are. And likewise, these marks are the second component. And when you think of it that way, putting it down as a vector, right, as a little thing with an arrow and a tail, right, that doesn't specify that we've made an inner product. It doesn't necessarily assert that, because we're not really talking necessarily about the lengths of things, although this is suggestive that we actually are talking about the lengths of things, right, because we have this ability to measure the magnitude of a vector. So in that sense, we have an inner product. You'll notice we didn't use this particular inner product, though. Do you see how this inner product ultimately was never applied here? We just immediately, by defining the sine and the cosine, we immediately divided everything out. But okay, fair enough. Let's say there is an inner product, and we can define these lengths, so we can define an area. I think that's probably right. But this is the tangent space in the examples that we will use the most in general relativity. We have a point in space-time, it has a tangent space, all the vectors live in that tangent space, and they're all connected to the origin of their little tangent space coordinate system, and the volume elements inside that tangent space. Remember, they're volume elements inside the tangent space, in a sense. We're not talking about volumes yet in space-time itself. And because of that, because of the way the math works out, you always have that those volume elements are equal to some formula involving the determinant of, well, it is the determinant of the of those vectors that form the parallelepiped. Notice this argument about the two vectors merging together to form a single line and the volume, the two-dimensional volume going to 0. It works just as well in this case, right? If I take vector B and I start bringing it down till it's the same as vector A, you lose a whole dimension. And once you lose a whole dimension, the volume of something is a product roughly of its dimensions. Well, if one dimension goes to 0, then the whole volume goes to 0. All that's left is the subvolume, this area of a plane, but that's still the volume of the parallelepiped, and the whole thing will be 0. And you would have to actually reduce this whole problem to one dimension less to capture a volume, say, in the plane in just one of the planes. Right, so to move forward now, we need to define the Levy Civita symbol. Now notice it's a symbol, right? It's not a tensor, it's a symbol, and that's going to matter a lot in a moment, or when we get to that part of some lecture. And that symbol I'm going to actually draw as a curly Q epsilon, which is supposed to be different than a non-curly Q epsilon. This is ultimately going to be the Levy-Civita tensor, right, which will build eventually. But we're not going to be building that now, and so we're just talking about the symbol itself. The Levy-Civita symbol takes indices, and it's going to take n indices. So I'm going to mark those indices I sub 1, I sub 2, ... I sub n. Now, I want to be able to count n indices, so I'm starting at 1. Now in general relativity, in the math we do there, we typically start at 0, and we would go to n minus 1. But I think for now, it's a little easier to make this case with the subscripted from 1 to n. And it is kind of annoying notation, right? Because you've got a subscript that is subscripted, right? And that's a bit of a nuisance. There is an alternative way to do this. I'll show it in a moment. But what do we mean by these subscripted subscripts? And the answer is we're dealing with permutations. We're dealing with permutations. So permutations. And a permutation is often written like this: 1, 2, 3 to n. Let me put a 4 in there. And then below those numbers are the permuted numbers, which might be, say, 2, 1, 4, 3, n, like that. Where the only changes are in these first 4. Let's just assume nothing changes here. So it's 4, 5, 6, all the way to n, and this is 5, 6, all the way to n. And so the permutation is a map that basically takes this top row and gives you the bottom row. And if we call that permutation sigma, then what we mean is that sigma 1 equals 2. Sigma of 2 equals 1. Sigma of 3 equals 4. And sigma of 4 equals 3. And sigma of 5 equals 5, to sigma of n equals n. Right? That's what we mean by a permutation sigma. The alternative way of doing this is saying that I sub 1 equals 2, I sub 2 equals 1, I sub 3 equals 4, I sub 4 equals 3, I sub 5 equals 5, to I sub n equals n. And the the subscripts we put on our Levy Civitas symbol could be the ones I've written down there, or it could be like this. Right. So those are two notations that are in pretty common use out there. And they have their advantages and disadvantages. This functional form can be useful in some occasions, and this form can be useful in a lot of other occasions. Also, this is a little bit bulky in the horizontal, right? This kind of flushes out the subscript a little bit, so you have to do a lot of writing, and it gets really long. On the other hand, here you're now subscripting subscripts, which gets a little tiny. So there's always these typographical and actually material differences between these two notations. So we will move kind of flexibly between these two notations. So I want to present that in a bit of detail. But now that we understand how to write down and draw the darn thing, what is it? So the Levy Civitas symbol, I'll do it this way: sigma 1, sigma 2, to sigma n. It's going to equal +1 if sigma is even, -1 if sigma is odd, and 0 if sigma is not a permutation. So since sigma is actually defined to be a permutation, this last one doesn't usually have to be in here. However, if you define it this way, I1, I2 to In, like that, you might tend to write a definition that looks like this: +1 if I1, I2, In is even permutation of 1, 2 to n, -1, same thing, but if it's odd, and then 0 if I1, I2 to In is not a permutation, right? Because for the case of sigma, we've actually defined it here to be a permutation, so the 0 case never exists, right? But here we've just said, well, this is a string of numbers between 1 and n, and if we, for example, we might want to sum through all the possibilities. So it may be that these subscripts end up having 2 of the same number, right? It could easily be that you end up with a case down here where I1 equals I3, or some other value of I, in which case you don't have a permutation because not all the numbers are permuted. You've duplicated numbers. And if that's the case, you end up with this condition here, and it just is 0. So these are ultimately identical, except that here we've defined that this is by definition a permutation, and here there's always the possibility that these numbers, I sub 1 and I sub 2, right, I could create a set of numbers where I sub 1 equals 2 and I sub 2 equals 2, for example, and it's not a permutation, in which case this is 0. That is so what is an even and odd permutation? I guess that's important to understand. And it has to do with, if we look at this example of a permutation, the number of interchanges that it takes to go from here to here will be either an even number or an odd number. In this case, it's an even number. If I interchange 1 and 2, I get the 2, 1, and if I interchange 3 and 4, I get the 4, 3, and everything else is the same. It took me 2 interchanges. So because it took me 2 interchanges, this thing here is an even permutation. If I then extended this, right, let's say I extended this, and I wrote, let's see, 4, 3, and then I wrote 6, 5, 6, 5, all the way to n, and everything else is the same up to n. Now it takes 3 permutations, and now it's odd, right? So it's always going to be even or odd. You can demonstrate that a permutation can never be both even and odd. The identity permutation, where nothing changes, where this is 1, 2, 3, 4, 5, 6, that's even because it's 0 interchanges. And any single interchange is odd. And so sigma is telling us whether or not the permutation is even or odd, and it returns a +1 if it's even and a -1 if it's odd. And the Levy-Civitas symbol, we've defined it with subscripts. Notice we've defined it with subscripts. That doesn't have to be the case. We can define it with superscripts, right? I can write E I1 I2 dot 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 IN. And for right now, I want you to understand that this Levy-Civitas symbol has the same values as this one. It's really identical, all right? The only way we're ever going to see this is with all the indices up and all the indices down. You cannot raise indices on the Levy-Civitas symbol using the metric tensor, right? G I1 prime I1 E I1 prime I2 does not equal something like let me get rid of that mess. It should be a little curly Q. Does not equal something like I1 I2. Does not equal that, right? There's no Levy-Civitas symbols that are split, right? Mix of covariant and contravariant. In fact, these things are neither covariant nor contravariant because they're symbols. They're not tensors. Only tensors can be covariant or contravariant. We will see, and we will study a little more about what exactly is going on with these guys later, but right now we just need to understand the definition. The fact that the version that has all upper indices is equal to the version that has all lower indices is a convention, right? There is an alternative definition where you multiply by -1 to the t, where t is the number of eigenvalues that are negative in the metric. We're not going to do that right now, and eventually we'll see why that convention would be useful. But for right now, we're not going to use that convention. Okay, so that's the Levy-Civitas symbol, and that's this guy, this Levy-Civitas symbol, both versions, the versions that have all lower indices and have all upper indices, are going to be able to help us define how to make a determinant. Now, related to the Levy-Civitas symbol is the generalized Kronecker, I'll just spell it with a K-R-O-N, Kronecker delta function. Right, so we know that the Kronecker delta function AB equals 1 if A equals B and it equals 0 otherwise, right? So the generalized Kronecker delta function looks like this. It's the same little delta function symbol, but at the top it has a sequence, or I1, I2 through IN, and then on the bottom it has a sequence, J1, J2, Jn. Now these are two different sequences, right? So you can actually think of them as a permutation from I1, I2 to IN to J1, J2 to Jn. And you could call that permutation, if you want, sigma. So in this case, to understand exactly what's going on, sigma of I1, whatever that is, equals J1. Sigma of I2 equals J2. So if I put in a string of numbers, right, if I put in a string of numbers, then, for example, say I decided that I1 equals 2, I2 equals 3, and I3 equals 1. And then say I said J1 equals 1, J2 equals 3, and J3 equals 2. Then the permutation I might want to consider is 2, 3, 1 to 1, 3, 2, like that. And I might call that sigma. Now notice this is a case where sigma actually could be not a permutation, right? If I screwed this up and I said I1 equals 2 and I2 equals 2, then I would have 2 and 2 here, and this permutation would take 2 to 1 and 2 to 3, and it wouldn't be a permutation. So that's an example where sigma might not actually end up being a permutation if you defined it through I1, I2, and I3, and J1, J2, and J3, and you screwed this up and you called that permutation sigma. It's not really a permutation. So that's a circumstance where if we went back to this definition, you might actually want to keep this line in there if sigma is not a permutation. Depends, right? In the beginning, if we define sigma to be a permutation, you'll never need that line. But here's a circumstance where you actually might. So the point is that the generalized Kronecker delta function is going to equal, the Levy-Civitas function of the permutation of this permutation, right? So if this permutation is even, then this guy here will get a +1. If this permutation is odd, this guy here will get a -1. If this is not a permutation, this guy here will be 0. So what we're doing is we're writing the entire permutation down as this index on the epsilon on the Levy-Civitas function. That's okay, right? Because the Levy-Civitas function, I1 through IN, well, this is understood to be a permutation. So if I name that permutation sigma, I can just as well call it var epsilon of sigma. So it's the same kind of concept. But notice that this thing is going to be 0 under the same familiar conditions. If this is not a permutation of 1, 2, 3 to n, then this could never be a permutation, so it'll be 0. If this is not a permutation, then this can't be a permutation either. And so all of these numbers up here and all of these numbers down here have to be the same, just not in the same order. And the nature of the difference between the order is given by some permutation, and that permutation is either even or odd. If it's even, this object, this generalized Kronecker delta function, is +1. If it's odd, this object is -1. Okay, so that's an important little thing to know that'll show up in some of our definitions about determinants. Oh, and one other way to think of it, too, is this interesting fact. Var epsilon of I1, I2 to In multiplied by var epsilon J1, J2, Jn. That equals the generalized Kronecker delta function I1 to In, J1 to Jn. And this makes me think, right, this is such an easy thing to remember. It makes me think that this whole thing was invented just to save space, right, because it actually cuts down the space in half. It does start jamming things a little bit vertically, but it's really not a difficult thing to understand. It's simply the product of two Levy-Civitas symbols for the same permutations that show up in the upper part and the lower part. All right, so now how do we make a determinant? So a determinant always involves a matrix, right? And this is a little bit off the reservation from our previous work because we kind of tried to get away from matrices. We're trying to understand tensors without using matrices. In fact, an interesting question came up about the stress tensor, right? The stress tensor of continuum mechanics. And the stress tensor is always taught to be a matrix, and it can be because the stress tensor is a rank 1-1 tensor, and a rank 1-1 tensor takes a vector and returns a vector, right? It absorbs a vector and it leaves a vector behind. So that's exactly like a matrix, right? A matrix takes a column vector and returns a column vector. And so it turns out 1-1 tensors are very, very good objects for working with regular linear algebra matrices. You can do linear algebra with 0-1 or 0-2 tensors. It's just a big mess. It's not the stuff we're normally used to doing. It involves rows of row vectors, right, or columns of column vectors, and these things are much harder to write down. But a 1-1 tensor ends up being these nice little square matrices. But in general, you really don't use matrix methods for the general algebras and the general study of tensors and vector spaces and tensor product spaces. But when it comes down to the determinants, you really are dealing with matrices. So, and therefore, we're going to talk about the matrices. We're going to talk about matrices and determinants in terms of matrices. Where they show up in our work, remember, is the linear transformations between bases, right? Those are always going to be represented by a matrix. And so that's a case where matrices do show up a lot in our work. In other words, the linear transformation of say some vector, whose components are A, that linear transformation is given by a matrix. And that's 100% a matrix all the time. So we can always talk about the determinant of linear transformations. And in fact, that's exactly where determinants show up the most in this subject, although they do show up in some other places. Anyway, so let's begin with this notion of a matrix and trying to find out the determinant of a matrix. So the determinant of a matrix, I'll do lambda, let's say I'll do I, J, like that. Right, so it's the determinant. I'll write these two indices here, but they're supposed to represent the full matrix, right? So you could argue that maybe I should write down determinant of lambda. Lambda is the linear transformation, and so that's another way you'll often see it written without these little indices. Either way, the determinant of this linear transformation, represented as a matrix, is going to be this var epsilon of I1, I2 to In, right? So we're going to assume that the dimension of this matrix is n, right? And therefore, because it's a a linear transformation from one basis to another, you know that it's going to be square, right? Let's see, A-R-E. It's going to be a square matrix. So, and then this will be lambda I1 and lambda I1, and this will be 1 lambda I2, 2 dot 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 to lambda I n n, just like that. And that that is it, right? That is a formula for the determinant of a matrix. Now notice we are summing over these indices, right? Right, so I have to take every combination of I1, I2, all the way to IN, and I make that sum. And in doing that, the overwhelming number of these will be 0, because there will be lots of duplications. There will be lots of times where I1 equals IK, and whenever that happens, it's not a permutation, right? And if it's not a permutation, it's going to be 0. It has to be a permutation of the numbers 1 through n. So that's one way of writing the determinant of a matrix. In fact, that's probably the most common way. There is, however, slight different forms of the same thing. And for example, here you'll see that these are fixed as 1, 2 through n. So we've established that we're going to use the sequence 1, 2, 3 all the way to n for this lower index here. But I can also get away with that, get away from that, and I can write it in this form. The generalized Kronecker delta function of, say, J1, J2 to Jn, I1, I2 to In, and then I do, let's see, I have to do I1, J1, lambda, I2, J2, all the way to IN, JN, like that. And that's another formula that works just fine. This allows you, for whatever reason you might want to choose a sequence JN. You just have to, it just complicates it because you add a sum over two things, right? And then remember that this is just the product of the Levy Civitas symbol with I1s downstairs and another Levy symbols with J1s upstairs, right? So this is the compact version of that. So that's a way of writing this matrix. Now, when you look in books to sort of study this and catch up, what you'll see generally is that they do these definitions for different configurations of indices on the matrices, right? They might do IJ or lambda JI, right? And all it is to get all of those other forms, you just adjust the Levy Civitas symbols so that the summations are correct. So you could have if the i's were downstairs here, you would have two Levy Civitas symbols with the epsilons being in the superscript position, right? And they'd be multiplied together. And so you can create all the different configurations. But this is the one we use the most. So when we do it, we like to keep these matrix indices for these linear transformations up and down. So we use these forms. But this is it. This is the definition. If you run this by a 3x3 matrix, you will discover that it is exactly the same as this this thing we did. Where did we do it? Here, right? This thing we did here, that'll be duplicated exactly. This will be duplicated immediately also. And this is just a shorthand way of doing it for any dimensionality. So 10-dimensional matrix, this is your answer. This is how it's done. And they're really big. I mean, there's a lot of permutations out there for a 10-dimensional square matrix. But the matrix has to be square. You have to have a square matrix to have any sense of a determinant. So that's our basic definition of a determinant, and that's the one we'll be using the most. But we do have to discuss a little bit about this square matrix thing. Imagine, for example, that we are, say we're studying the fifth exterior power of a vector space V, and the dimension of that vector space V equals 10. Now this is totally contrived, right? This is just to get the numbers up, right? But you could imagine that if that were the case, we might end up with an array of numbers that is essentially maybe not 10. Let me cut that back one. Let me cut that back to 9, say. We might end up with a 9 by 5 matrix, right? Say, and such a matrix would be, gosh, you'd have to go A, B, C, D, E, and then F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and then maybe little letters A, B, C, D, E, F, G, H, I. Maybe I shouldn't have taken such a big example. J, K, L, I don't want that capital L, L, M, N, let's see, L, M, N, right? And then O, P, Q, R, S. Phew. All right, so there's this matrix, right? And so what am I talking about? I'm talking about, say, so the fifth exterior power and dimension 9. So these might be 5 vectors, you know, each, and these would be the components of those vectors stacked up in column form. I did it in row form last time, but I guess these would be the components of 5 different vectors in column form. Such an object might arise in this study of this, for example, because every member of the fifth exterior power can be written, let's see, it can be written as E1 wedge, well, EA wedge, EB wedge, EC wedge, ED wedge, EF, where I is an element of the first exterior power of V, right? It's a one form. So the everything in the fifth exterior power is expressible as a sum of these guys, right? Where each of these are one forms wedged together 5 times, right? That's, if you go back to our study of the fifth exterior power, that's what it is. So presumably there's some component T, A, B, C, D, I guess I did F here, and that component, for example, would, this is a member of the fifth exterior power. So there's circumstances that we'll get into later where, because there are 5 of these here, we might want to stack up 5 different vectors in a matrix, and then the dimensionality of each of those vectors is 9. So that explains why we might end up with an object that is a 9 by 5 vector, and we will later. We will a bit later. So so now let's, looking at this matrix, you can't take the determinant of such a thing, right? Because it's not square. But buried inside it are plenty of square matrices. For example, this this matrix here, right? That's 5 by 5, and so is this one, right? That's 5 by 5, and this bottom one here is 5 by 5, right? So there's 3 5 by 5 matrices, and obviously there's more than 3 of those available, right? There's also this 2 by 2, right? And then there's this 2 by 2, and there's this 2 by 2. So there's a lot of 2 by 2s in here, right? So those matrices are around. In fact, all you have to do is cross out rows and columns enough, and you will end up with matrices that are 5 by 5 all the way down to 1 by 1. So I could cross out, say, this row, this row, this row, and let's say this row. And what's left is a 5 by 5, right? It's the 5 by 5 includes this row here, this row here, this row here, that's 3, and then these 2 rows here. and I could rebuild that matrix as a 5 by 5 matrix, right? Likewise, I could cross out that row, say that row, and that row, and I would be left with these two rows. I think I crossed out one too many rows. I'd be left with, well, I'd be left with this. That's a 5 by 5 matrix, right? So I can make all these crosses out, and I can cross these. Well, let me do another example here. I could cross out this, and this, and this, and this, and then I could cross out that column. And what's left is a 4 by 4, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4, right? So that's my 4 by 4 matrix left over. The point is all of these matrices are square, and you can take the determinant of any one of them, and let me get rid of these, and you end up with a square matrix with a determinant. This process is called, each of these little matrices, these submatrices, are called a minor. A minor. The minor is actually the determinant of some submatrix, right? And the way we identify the determinant of a submatrix is I'll call it, say, well, let's say this matrix here is called M, right? So M is this thing here, right? M is this matrix here. So you can't take the determinant of N because it's shaped funny, but you can take the determinant of M if you include certain rows and columns only. So let's identify, say, one of these 5 by 5 matrices, right, where we exclude, say, this, 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 and this, right? So the rows that we include are going to be the first row, so we'll include the first row, we'll include the third row, we'll include our fifth row, sixth row, and the seventh row. And the columns we will include are all the columns, 1, 2, 3, 4, 5. And this symbol here is going to represent the determinant of that submatrix that is described by what this elimination, or the inclusion of these rows, and the inclusion of these columns. You build that matrix up, it's a 5 by 5, you take its determinant, and that is the minor associated with these sets of numbers. So likewise, I've got to undo this so I can redo it again. So if I do too much writing. So now, say I might want the minor of something smaller, say 1, 3, and 4, and 2, 4, and 5, right? The minor of 1, 3, 4, 2, 4, 5. So the only ones that are in are 1, 2 is out, 3 is in, 4 is in, 5 is out, 6 is out, 7 is out, 8. These guys are out. And 2, 4, and 5. So 2 is actually in, so 1 is out, 3 is out, and what's left over is going to be the determinant of, I could actually write this one down, B, D, E, L, N, O, and Q, S, T, like that, right? So that's the minor. So we'll be using these minor concepts quite a bit in some of our work, and this notation will be important. So a concept closely related to the minor is that of the cofactor. And the cofactor is something that also should be familiar from linear algebra days, even in high school math, where we're always dealing with square matrices. I think I'll just draw one out, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Right, so here's a matrix, right? And we always knew that the cofactor was going to be, it was going to be the number we acquired by crossing out a single row and a single column and forming the number minus 1 to the row plus column times the determinant, in this case, of what's left over, which is A, C, D, I, K, L, M, O, P. And notice this only made sense for a square matrix, right? Because crossing out one row and one column kept everything square. And this number was the cofactor. And using the cofactor, you could find, calculate the determinant of the 4x4 matrix by calculating 3x3 matrices. And it was a bit recursive, but nevertheless, it was a formula that we learned. But now we know that this notion of the minor, we could actually say this is minus 1 to the I plus j times the minor, I guess this would be the 2 minor, right? Where we, it'd be the, it'd be the way we did this before, it would be the 1, 3, 4, 1, 3, 4 minor, right? So that would be our new notation for this, right? So with any square matrix, however, we can create all kinds of different minors. The question is what will the cofactor be for minors that aren't just one smaller than the size of the matrix? So this is always going to be n by n. These minors here, and the way we've always learned, are going to be n minus 1 by n minus 1. But we can have all these different minors, but once we have all these different minors, then the question is, what's this thing going to be, right? This thing makes perfect sense if you're eliminating one row and one column. In fact, it doesn't even make too much sense right now if we use this notation, because we're including rows here, and these are excluded, right? So it's already a little weird. I mean, it makes sense. The remaining rows go in this notation here, and the rows excluded go there. I mean, that's not too hard to understand. But it does become a bit of a puzzle if, for example, we went for, instead, we crossed out 2 rows, right, like this, say. And then we know that the minor will be minor 1, 4, minor 1, 4 again, I guess. And that's going to equal the determinant of A, D, M, P, right? But there's probably some factor here. Now we don't quite know. Do we just add up all of the numbers? Minus 1 to the I plus j, so it'd be 2, 2, and 3, and 3. So there is a general formula for this, and the general formula, of course, this only worked for square matrices, right? This only works for square matrices, because what's left over when you there's a complementary minor, right? For every minor, there's a complementary minor, and that complementary minor is going to loom large in what this factor is. So let's do this example again. A, B, C, D, E, F, G. All right, so we have a 4x4 matrix. It's important that we're now talking about square matrices. So this is stuff that's only pertinent to the linear transformations that we're talking about. So with this square matrix, we might talk about the minor, the 1, 3, 3, 4 minor, right? Which would be the determinant of, and now we look, we say, okay, row 1 and 3 are in, and rows 3 and columns 3 and 4 are in. So that would be the determinant of C, D, K, L, like that. So that is the 1, 3, 3, 4 minor. Now the complementary minor is going to be the minor that is of the rows that weren't in the last time, and there will always be a complementary minor. In this case, it'll have the same size. So it'll be the 2, 4, 1, 2 minor, which will be the determinant of EFMN, EFMN. Let's make sure I got that right. So the rows that are in are 2 and 4, and the columns that are in are 1 and 2, so it's EFMN. So that's good. And just to make sure, the first one was the rows that are in are 1 and 3, and the columns that are in are 3 and 4. So that's CD KL. CD KL. Why don't I have a K here? That should be a K. Okay, so there's some examples of those. Those are two complementary minors in the sense that they reflect determinants of two different minors, but they are the minors that complement the others because of the opposite rows being in and out. If we increase this W, X, Y, Z, and then I guess I could call this last element T, W, X, Y, Z. I'll call it 1, the number 1. How about that? So now I have a 5 by 5 matrix. So in this case, the 1, 3, 3, 4 minor is still CD. Oops, this should be a K, right? CDKL, but the complement now, this is no longer the complement. The complement has to be 2, 4, 5, 1, 2, 5, right? So that complement is the determinant of what's in. What's in is 2, 4, 5, and 1, 2, 5, right? So what's in is E, F, R, M, N, T, and W, X, 1. So it's the determinant of E, F, R, M, N, T, W, X, 1. So in that case, the complement is not the same, the complementary minor is not the same as the, not the same size as the minor, as its complement, right? There's a 2 by 2 and a 3 by 3. Anyway, the point of all this is that the cofactor of a particular minor, I'll call it I1 through IK, and J1 through JK, we're dealing with an n by n matrix, right? So the cofactor of a particular minor matrix is going to be defined through the following formula: 1 over n minus k. Right, in this case, n equals 5, and here k equals 2, right? So n minus k factorial, and then we get the generalized Kronecker delta function for I1 all the way through IN, and J1 all the way through Jn, and then I got to write down the relevant matrix elements, right? And the matrix element is going to be the matrix element of IK plus 1, JK plus 1, and I've got to erase this, otherwise I'm going to get in my own way, dot, 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 M, I, N, J, N. Phew. So this cofactor expression, ultimately you can see this part here, right, is the determinant of the complementary matrix, right? Because the original minor just goes from 1 to k, so I pick out a k-dimensional minor, but this starts the sequence at k plus 1 and goes to n, so it takes up the rest of the numbers. That is, and that combined with this Kronecker, generalized Kronecker delta function, if I remember right, or if I go back to this formula, that is the determinant of a matrix, almost. There's this 1 over n factorial factor, but we're dealing with n minus k, right? It's n minus k. So what ends up happening here is that this whole feature here is the determinant of the cofactor minor matrix. And then there's there's a sign that is equivalent to this thing right here, but for a generalized condition. So this cofactor is very important. It exists, right? It exists for all possible minor matrices, not just the ones that we're familiar with from linear algebra, where we just crossed off one row and column. But if you do cross off just one row and column, it reduces to the same thing. So in other words, that's saying that the cofactor of, if you have a 4x4 matrix, the complementary matrix of a 3x3 minor is just a single element, right? So that's totally legitimate. It adds up to n, so that should work out just fine. And so this expression is this generalization of the cofactor expression. Oh, wait a minute. I think I said that the other way around, right? If you go back to this, the cofactor, we're dealing with the cofactor of f, right? The cofactor of f, the complementary minor of the minor f. The f is considered as a 1x1 minor. Then the complementary minor is going to be the 3x3 with f crossed out, which is this thing here. And the appropriate sign just reduces to something very simple. So that's what's going on here, is that we're finding the determinant of the complementary matrix. So that's the minor. The minor is a matrix. The minor is a determinant of a matrix. The cofactor of that minor is the determinant of the complementary matrix, and then there's a little bit of sign adjustment here that depends on these permutations, on this particular set of numbers here. So, and the reason it depends on these numbers here is because you'll notice this delta function includes all of the indices from 1 to n, right? This is from k plus 1 to n, but this is from 1 to n entirely. So the first k on this side, you might think that this doesn't add up, but the first k indices here are established by your choice of what cofactor you're looking for. So there's really only k plus 1 to n free indices on this thing over here. So I told you that in order to tell you this. I want to show you this important formula that we eventually use. There's a lot of weird formulas with determinants, so keeping track of them all it's not realistic to think you could keep track of them all, but usually with formulas and things, if you see them for the first time, it's more annoying than if you've heard about them or you're aware of them. So if I write this formula for the minor of a matrix, or the minor of a particular minor of a square matrix, right, so JK, so remember I'm dealing with an n by n matrix out there, and this is a k by k minor of that matrix, so it's the determinant of something, right? This is also equal to the determinant of the matrix as a whole multiplied by the cofactor of the inverse matrix with the same with the same rows and columns involved, but they're reversed. It's sort of, I guess, the transpose, I1 through IK. So this actually turns out to be a handy formula. There will be times where we need to know the minor of a matrix, and we can make a substitution with the determinant of the matrix multiplied by a cofactor associated with the inverse matrix, where the included rows and columns of the original matrix are essentially transposed in the this inverse factor. So this is a formula that we will eventually use when we work with as we get a little bit deeper into our study of forms. Not too dissimilar to this is Laplace's formula. So the determinant of a matrix M is the sum from, I guess, let's see, I equals 1 to n, where n is the dimension of M, times of the cofactor of m, let's see, I, j times m, I, j, where we can choose j, right? So I is getting summed over from 1 to n, but j is not specified. So we can pick a j. So we can do this for, say, j equals 1 or j equals 2, and then run the sum. And it doesn't really matter what we choose for j, but it's an option, so we leave it as a letter. So that's the famous, this is what you learned in algebra about a way of calculating the determinant. I understand it's not the most efficient way of doing it, but if you triangularize the matrix first, it actually becomes very efficient. Anyway, that's Laplace's formula, and we'll also use that. This is, I guess, a formal way of writing down Laplace's formula. And here, now you're dealing with the cofactor of, if you look at it, actually, there's really no reason for me to separate this. This is a matrix element, right? This is a matrix element, so I would write that M, I, and then J with a little bit off to the right. But the cofactor is just M, I, J, straight up and down. Well, actually, I'm sorry, that's not true. It's the cofactor of an element of the matrix, right? So it's the cofactor of a 1-by-1 matrix, right? Well, we know that that cofactor is going to be an n minus, it's going to be the determinant of an n minus 1 by n minus 1 matrix, which is exactly what we remember from algebra, right? You would take out a row, you would take out a column, you would have everything left over that you would take its determinant, and then you multiply it by that matrix element, and you include a factor of minus 1 at the I plus j, and then you did this all the way across for the entire row, and that's what this sum is. It's going across the entire row. This cofactor here is the determinant of everything left over after you cross out a line and a column, plus this factor is also embedded in that cofactor, and then multiplying by the element, well, that's what this part is here. So that's the old Laplace's rule for calculating the determinant, written in the form that we will use it eventually. And another formula that's important for us that we'll be using when we study the Levy-Civitate tensor is a formula that looks a little similar to the definition of the determinant and is definitely related, but is not quite the same formula. This product with the Levy-Civitate symbol summed over that, Levy-Civitate symbol, that equals the determinant of lambda times the Levy-Civitate symbol on J1 through Jn. And this is actually an important formula to understand that to understand coordinate transformations later on. But what it allows us to do is we take a product of matrices with a Levy-Civitate symbol, and we can replace all of this with the determinant of these matrices multiplied by the Levy-Civitate symbol associated with these other indices. Right? And you can see how helpful this might be. If these are coordinate transformations, or if lambda is a coordinate transformation, I will be one reference frame and j will be the other, so I will be the prime frame and j will be the unprimed frame, or vice versa. And we'll be able to basically take a Levy-Civitate symbol from a unprimed frame, or the I frame, and convert it into one in the j frame with this formula. And so that's going to be very useful also, and we'll slip that one in when we study the Levy-Civitate tensor. And so the last thing to remember about determinants and these linear transformations is, well, linear transformation, in this case we've been calling it lambda, it's a square by square matrix, right? So it's an n by n matrix, so you know that it has a characteristic polynomial. And I won't go through how to calculate that. I presume you remember it, but ultimately in the end the characteristic polynomial, let's see, it goes p of lambda equals the determinant, right? Again, this is why it's interesting here. It's because it's the determinant of lambda minus, well, usually it's little lambda given by then the identity matrix, right? So, you know, this is where the usual thing where you subtract off lambda from the identity elements, calculate the determinant, and what's left is a polynomial that usually looks like minus lambda to the n plus, and then there's this number mu1 times minus lambda to the n minus 1, and this goes all the way down to mu of n minus 1 times minus lambda plus mu of n, right? And so that's how you can ultimately write the characteristic polynomial. It's always an nth degree polynomial. If you have an n by n matrix, you're going to have an nth degree polynomial, and that'll be the characteristic polynomial. The point is that all of these numbers, mu1 all the way through mu n, mu1 dot 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 to mu n, those are invariants, right? So this linear transformation will always have these invariant numbers associated with it, and it'll always have n different invariant numbers associated with it. The point is that the last invariant number is in fact the determinant of lambda. So the determinant of lambda is one of these invariants. It turns out the first invariant is the trace of lambda. So that invariant is familiar. And then all these invariants in between are more esoteric combinations of the trace and some other things that they're just more and more sophisticated things. These are the two that you should keep in mind, though, is mu1 and mu(n) are these two invariants. And that becomes important later, too. Okay, so that was a really rapid dump of things about determinants to remind you. I think one of the most important things is this concept here, that the determinant is related to the area, or I should say the volume of a parallelepiped. Area is just the example we've done is 2 by 2, so the volume of a two-dimensional thing is an area, so that's why I slip and use the word area. But the volume of a parallelepiped with vectors associated with, that's one of the ways of understanding a determinant. And showed that the volume element, or not the volume element, the determinant formula actually matches this idea where one of these parallelepiped sides becomes more similar to another one, and if this vector fell into that plane, then the volume would go to 0. So that worked. Then we talked about the Levy-Civitas symbol, which is not a tensor, despite the fact that it has indices. Right, and we talked about how the permutations worked and how it's defined, and then we talked about the generalized Kronecker delta function, which is really just sort of a notational collapse of the product of two Levy-Civitas symbols, right? And then we just these are the definitions of the determinant, right? This is how you calculate a determinant for any dimension, And we talked about the minors, how to get a minor out of any matrix, square or not. Then we talked about cofactors, and that was an example of a cofactor for a 1 by 1. The cofactor of a 1 by 1 matrix, right, is just cross out the one row and one column of the 1 by 1 matrix, and the determinant of what's left times this factor is the classical cofactor. And then I taught you how to generalize the notion of a cofactor to any minor, every minor matrix of a square matrix. So you got to start with a square matrix for cofactors to make sense. But if you have a square matrix, any minor of that square matrix has a cofactor, and it's given by this expression. And then this is the Laplace, the way to calculate the determinant using Laplace's method, written in terms of the cofactors. And of course, in this case, the cofactors are always of 1 by 1 matrices, so this duplicates our elementary algebra expression, but we still use this in our proofs later on. And then I taught you this formula that relates the Levy-Civitas symbol in two coordinate systems. As it is, it's just an arbitrary matrix formula that expresses Levity-Civitas symbols with two different sets of indices, but ultimately we'll use that to transform it between coordinate systems. And then we talked about the characteristic polynomial. So that's a rapid run-through of the determinant. Obviously, if any of these things are really, really hard for you to understand, just go back to a linear algebra book, a good one, and you can catch back up really quickly. And we will use these things as we march through a little bit more of a detailed study of the exterior algebra.